In this video, we're going to be talking about hypothesis testing using a single sample. Specifically, we're going to be talking about errors in hypothesis testing. When you perform a hypothesis test, you make a decision. You either reject the null hypothesis or you fail to reject the null hypothesis. And when you make one of these decisions, there's a possibility that you could be wrong, that you made an error. Each could possibly be a wrong decision. Therefore, there are two types of errors. A type 1 error is the error of rejecting the null hypothesis when the null hypothesis is true. So the probability of a type 1 error is denoted by the lowercase Greek letter alpha. And alpha is called a significance level of the test. So using an example from a previous video, if our null hypothesis was that a defendant was innocent and we rejected the null hypothesis when it was true, then that means that the jury found that defendant guilty when in fact they were not guilty. A type 2 error is failing to reject the null hypothesis when the null hypothesis is false. So that would be like saying that the defendant was not guilty when in fact the defendant was guilty. So the probability of a type 2 error is denoted by the lowercase Greek letter beta. Here's another way to look at the types of errors. So we have a grid. So suppose that our null hypothesis is true and we fail to reject it. What type of decision did we make? We made a correct decision. Well, suppose that the null hypothesis is true and we reject it. What type of decision was made? We made a type 1 error. So suppose that your null hypothesis is false and we reject it. What type of decision was made? A correct decision was made. And suppose that your null hypothesis is false and we fail to reject it. What type of a decision was made? This is a type 2 error. Let's look at some examples. So here the U.S. Bureau of Transportation Statistics reported that for 2009, 72% of all domestic passenger flights arrived on time, meaning within 15 minutes of its scheduled arrival time. So suppose that an airline with a poor on-time record decides to offer its employees a bonus if in an upcoming month the airline's proportion of on-time flights exceeds the overall 2009 industry rate of 0.72. So let's state the hypotheses here. Our null hypothesis is that P equals 0.72. And our alternative hypothesis is that P is greater than 0.72. So now we're going to state a type 1 error in the context of this problem. So a type 1 error would be that the airline decides to reward the employees when the proportion of on-time flights doesn't exceed 0.72. A type 2 error in this context would be that the airline employees don't receive the bonus when they deserve it. Let's look at another example. In 2004, Vertex Pharmaceuticals, a biotechnology company, issued a press release announcing that it had filed an application with the FDA to begin clinical trials of an experimental drug, VX-680, that had been found to reduce the growth rate of pancreatic and colon cancer tumors in animal studies. So the data resulting from the planned clinical trials can be used to test. So we're going to say that mu is the true mean growth rate of tumors for patients taking the experimental drug. So our null hypothesis would be that our mean is equal to the mean growth rate of tumors for patients not taking the experimental drug. And our alternative hypothesis would be that the mu is less than the mean growth rate of tumors for patients not taking the experimental drug. Remember that our mu was the true mean growth rate of tumors for patients taking the experimental drug. So we're going to state a type 1 error in the context of this problem. So a type 1 error would be to incorrectly conclude that the experimental drug is effective in slowing the growth rate of tumors. So what is the potential consequence of this error? Well, a potential consequence of this error is that the company would continue to devote resources to the development of the drug when it really isn't effective. So what is a type 2 error in the context of this problem? Well, a type 2 error would be to conclude that the drug is ineffective when in fact the mean growth rate of tumors is reduced. So what's a potential consequence of this error? Well, a potential consequence of making a type 2 error here would be that the company might abandon the development of the drug that was actually effective. So what is the relationship between alpha and beta? Well, the ideal test procedure would result in both alpha equaling 0, so a 0 probability of a type 1 error, and beta equaling 0, 0, the probability of a type 2 error. This is impossible to achieve since we must base our decision on sample data. Standard test procedures allow us to select alpha, the significant level of the test, but we have no direct control over beta. So selecting a significance level alpha of 0.05 results in a test procedure that, used over and over with a different sample, rejects a true null hypothesis about 5 times out of 100. So why not always choose a small alpha, like alpha equals 0.05 or alpha equals 0.01? That's a great question. Let's look at a little example to help us out. So we're going to consider the following hypothesis, that p equals 0.5 and that p is greater than 0.5. Now suppose that this normal curve represents the sampling distribution for p hat when the null hypothesis is true. This is the part of the curve that represents alpha, or the type 1 error. Now if the null hypothesis is false, and the alternative hypothesis is true, then the true proportion is believed to be greater than 0.5. So the curve should really be shifted to the right. And this tail would represent beta, the probability of failing to reject a false hypothesis. So let's suppose that our alpha this time equaled 0.01. So if the null hypothesis is false and the alternative hypothesis is true, then the true proportion is believed to be greater than 0.5. So the curve should really be shifted to the right. And this tail would represent beta, the probability of failing to reject a false null hypothesis. Notice that as alpha got smaller, beta got larger. So how does one decide what alpha to use? Well, after assessing the consequences of a type 1 and a type 2 error, you're going to identify the largest alpha that is tolerable for the problem. Then you're going to employ a test procedure that uses its maximum acceptable value rather than anything smaller as the level of significance. Because remember that using a smaller alpha increases our beta. Let's look at an example. So the EPA has adopted what is known as the lead and copper rule, which defines drinking water as unsafe if the concentration of lead is 15 parts per billion or greater, or if the concentration of copper is 1.3 parts per billion or greater. So the manager of a community water system might use lead level measurements from a sample of water specimens to test the following hypothesis. If our null hypothesis is that the mean equals 15 versus the alternative hypothesis that the mean is less than 15. So let's state a type 1 error in the context of this problem. Well, a type 1 error is going to lead to the conclusion that a water source meets the EPA standards when the water is actually unsafe to drink. So what is the consequence of this error, this type 1 error? Well, there are possible health risks to the community. So what about a type 2 error in this context? Well, for this problem, a type 2 error leads to the conclusion that a water source does not meet the EPA standards when the water is really safe. So what is the consequence of a type 2 error? Well, so the community might lose a good water source. So now we need to ask ourselves, which type of error has a more serious consequence? Now, since most people would consider the consequence of a type 1 error a little more serious, we would want to keep our alpha small to select a smaller significance. So we're going to select a smaller significance level, so our alpha would equal 0.01. Let's take a look at another example. So here a researcher wants to conduct a study to test whether listening to soothing music for 20 minutes helps to reduce diastolic blood pressure in patients with high blood pressure compared to simply sitting quietly in a noise-free environment for 20 minutes. 100 patients with high blood pressure at a large medical clinic are available to participate in this study. So we're going to do two things. First, we're going to propose a design for this study to compare these two treatments, and we're going to look at 3 different design options. Then we'll do part B, which is the null hypothesis for this study, is that there is no difference in the mean reduction of diastolic blood pressure for the 2 treatments, and the alternative hypothesis is that the mean reduction in diastolic blood pressure is greater for the music treatment. If the null hypothesis here is rejected, the clinic will offer this music therapy for a free service to their patients with high blood pressure. Then we're going to describe a type 1 and type 2 error and the consequences of each in the context of the study, and discuss which you think is more serious. So let's begin with the designs. So approach 1 would be a paired design. So here each subject will receive both treatments with a suitable length of time between the treatments. So in order for the treatments to be randomly assigned to the subjects, or the order of the treatments rather, would be randomly assigned to the subjects. So for example, for each patient you're going to flip a coin to determine which treatment will be administered first. You're going to measure their diastolic blood pressure and then have the subject sit quietly for 20 minutes in either a noise-free environment or in a room where soothing music is played, depending on which treatment was selected at random based on the coin flip. At the end of the 20 minutes, you're going to measure the diastolic blood pressure again and compute its change, so the after minus the before. Then after a suitable period of time, you'll repeat with the other treatment. When the data has been collected, the difference in the music minus the noise-free room and the change in diastolic blood pressure will be computed for each subject. And then a paired t-test will be run to see if the mean difference is significantly different from 0. Our second approach is a matched pairs design. So we're going to measure the diastolic blood pressure for each of the 100 subjects and then form 50 pairs based on these readings by pairing the 2 with the highest diastolic blood pressure and then the 2 with the next highest, and so on. For each pair, we're going to toss a coin to determine which member of the pair will be assigned to group 1, and then assign the other member to the pair to group 2. For group 1, we're going to measure the diastolic blood pressure, then have the subject sit quietly in a noise-free environment for 20 minutes, and then measure the diastolic blood pressure again and compute its change, so our after minus our before. For group 2, the plan is the same, except that they will sit for 20 minutes in a room where soothing music is played between blood pressure measurements. When the data has been collected, the difference, so the music minus the noise-free room, will be measured for the change in diastolic blood pressure. It will be computed for each pair, and then a paired t-test will be run to see if the mean difference is significantly different from 0. And our third option is the completely randomized design. This is not as good of a choice as the 2 previous approaches, but because of the large number of subjects available for each treatment group, it's considered an acceptable solution. So you're going to assign the 100 patients numbers from 00 to 99, and from a random number table you're going to select 50 unique numbers, and the patients with the selected values will form group 1. The remaining 50 patients will form group 2. For group 1, you're going to measure the diastolic blood pressure, then have the subject sit quietly in a noise-free environment for 20 minutes, and then measure the diastolic blood pressure again. For group 2, the plan is the same, except that they will sit for 20 minutes in a room where soothing music is played between blood pressure measurements. Let's now look at Part B. Remember, in Part B, the null hypothesis for this study is that there is no difference in the mean reduction of the diastolic blood pressure for the two treatments, and the alternative hypothesis is that the mean reduction in diastolic blood pressure is greater for the music treatment. So if the null hypothesis is rejected, the clinic will offer this music therapy as a free service to their patients with high blood pressure. So we are going to now describe a type 1 and a type 2 error and the consequences of each in the context of this study, and discuss which one we think is more serious. So I want you to do that on your own. So go ahead and push pause, and when you're done, push play, and let's see if you were right. So a type 1 error would be concluding that soothing music does not reduce the mean diastolic blood pressure compared to sitting quietly, when in fact it does. The consequence of this type of error is that the clinic will offer music therapy when it's not effective. The type 2 error would be soothing music does reduce diastolic blood pressure compared to sitting quietly, but we fail to detect this and conclude that it does not. The consequence is this type of error, and for this type of error, is that the clinic will choose not to offer music therapy when it would have been effective. So which type of error is more serious? A case can actually be made for either type of error in the situation. So as a student, you can take either side as long as you give reasonable justification. So for example, a student might say that a type 1 error is more serious because it will cost the clinic money with no benefit. Or you might say that a type 2 error is more serious because the clinic will miss an opportunity to improve the health and well-being of its patients.